In this lesson, we're going to look at logarithm 2. The most commonly used logarithms are logarithms to base 10, hence they are called common logarithms. Any positive number can be expressed as a power of 10. For example, 10 is equal to 10 to the power of 1 or raised to the power of 1. 100 is equal to 10 raised to the power of 2. 1000 is equal to 10 raised to the power of 3. These powers of 10 are called logarithms to the base 10. So 1, 2, 3, they are logarithms to the base 10. So, or to the base 10, that is number is equal to 10, and then the power is the logarithm. So the logarithm of 1 to base 10 is 10. The logarithm of 2 to base 10 to the base 10 is equal to 100. And 1000 is equal to the logarithm of 3 to the base 10. Logarithms of numbers can be obtained from four-figure tables. To find the logarithm of a number, we need to express the number in standard form first, and then apply the multiplication law of indices. For example, 850.9 when expressed in standard form is equal to 8.509 times 10 raised to the power 2 in standard form. But from our tables, log 8.509 is equal to 0.9299 from log tables. Therefore, 850.9 is equal to 10, which is 10 equal to, from what we have here, the number which is 850.9 equal to 10 raised to the power, and the power is the logarithm. So 10 from our log tables, 850.9, 0.9299, so 10 raised to 0.9299 times 10 raised to power 2. This power 2 is what this number expressed in standard form. So this 10 raised to power 2, and then this other part is the log value of 850.9 from tables. So now we're going to apply the multiplication law of indices, because we have two bases being the same, this base 10 and this base 10, and then we have multiplication between the two bases. So when this occurs, the principle we apply is the multiplication law of indices, and that is we're going to add the powers. So 10 raised to 0.9299 plus 2, which gives us 2.9299. And of course, therefore, log 850.9 is equal to 2.9299. So something to note that in common logarithm, the base number, that is 10, is normally omitted. So thus log 850.9 is the same as log 10 log 850.9 to the base 10. So because it's common logarithm, we usually omit the base 10, but it's still the same thing. The logarithm of a number contains two parts. The logarithm of a number contains two parts. The first part is an integer part, also called the characteristic, and B, a decimal fractional part, also called the mantissa, which can be found from the log table. So e.g., log 850.9 is equal to 2.9299. So discover that the log value of 850.9 has two parts. We have the whole number part, which is called integer or characteristic, the whole number part, which is called the integer or characteristic, and then we have a decimal point, and after the decimal point we have another part, groups of numbers, which we have a group of numbers which is known as a decimal fraction or mantissa. So after the decimal point, every other number is called mantissa. They collectively are called mantissa or decimal fraction. Okay, so in a nutshell, the logarithm of a number contains two parts: A, an integer part, also called the characteristic. So the characteristic is usually the whole number part. Then B, a decimal fractional part, also called the mantissa, which can be found from the log tables. So these are the two parts that the logarithm of a number is made up of. Okay, so we can find the characteristic of a number if we express the number in standard form. So the best way to get to find the characteristic of a number is to express that number in standard form. Like when we got to this point, 850.9, 850.9. So when we express this number in standard form, this is what we got: 8.509 times 10 raised to the power 2. So this power 2 is our characteristic. That's how we get to know the characteristic of any number that we want to know the logarithm value of. So we can find the characteristic of a number if we express the number in standard form. By the way, I have a video or a playlist on standard form. So if you want to know how to express numbers in standard form, you can check that playlist out and watch the videos. So we can find the characteristic of a number if we express the number in standard form. So the power of 10 gives the characteristic of the number. For example, 850.9 is equal to 8.509 times 10 raised to the power 2. This is in standard form. What we have done here, we have expressed this number in standard form. So the power of 10 is 2. So the characteristic is 2. Similarly, 6.895 is equal to 6.895 times 10 raised to the power 0. So our characteristic here is 0. B, 68.95 is equal to 6.895 times 10 raised to 1. So what's our characteristic? Characteristic in B is 1. Why? Because the power of 10 is 1 here when this number is expressed in standard form. C, when 689.5 is expressed in standard form, the power is 2, and therefore our characteristic is 2. So what you need to note is this. Note that in A to C, the characteristic is always 1 less than the number of digits in the integer part of the given number. The characteristic is always 1 less than the integer, less than the number of digits in the integer part of the given number. So if you are given 342.8, this integer part, the whole number part, there are 3 digits. So the characteristic will be 1 less than that. So since there are 3 digits, 3 minus 1 will give you 2. So the characteristic will be 2. When you have 7, 4, 8, 9, 6, what we're using will be the characteristic. How many digits do you have here? There's no decimal point, so it's entirely whole. Everything is entirely whole. So how many digits do you have? 1, 2, 3, 4, 5. So 5 minus 1 is equal to 4. So that will be our characteristic. So when you want to express this as in standard form, rather, what do? The decimal point is here. So 0, 1, 2, 3, 4. That becomes 7 points. So you say 7.4896 times 10 raised to 4. So 4 is the characteristic. And if you have 7, 2, 3, 4, 5, 8.72, and you want to express in standard form. When you want to express it in standard form, the integer or the whole number part, this is the whole number part. Now, how many digits are there? This is 1, 2, 3, 4, 5. So 1 less than the number of digits in the integer part will give the value of the characteristic. So we have 5 digits here. 1, 2, 3, 4, 5. 5 minus 1 is equal to 4. So let's express it in standard form. 1, 2, 3, 4. So that will give us 7.235872 times 10 raised to 4. So 4 is the characteristic. So that's how we get the value of our characteristic. Always gotten from the expressed, always gotten from the power of 10 when the number is expressed in standard form. So, and always note that it's always one less than the number of digits in the integer part of the given number. So all you need to do if you want to express it in standard form is just take a look at the number of digits in the integer part and then count the number of digits and then subtract 1 from it, and then you get the characteristic. It's as simple as that. We are to use tables to find the logarithms of the following. So A, 6.895. Remember that to get the logarithm of a number, we understand that the logarithm of a number has 2 parts, and one of it is the integer or the characteristic, and then the other is the mantissa, which is also the fractional, the decimal fractional part rather. And so first thing first, to get the characteristic. To get the characteristic is without expressing the number in standard form, or we just determine the value of the characteristic by noting that the characteristic is gotten by counting the number of digits that make up the integer part and then subtracting one from it, because it's always going to be one less than the number of digits that make up the integer or characteristic. The integer part, which is the whole number part of the number. So here, if we count, we only have one digit here in the integer part. So 1 minus 1 will be 0. So our value will be 0. The characteristic will be 0 point. The another way to go about it is just express it in standard form. 6.895 in standard form is equal to 6.895 times 10 raised to 0. And 0 is our characteristic here, which is the power of 10. And the next thing is to look for the value of the mantissa by looking up this value in our 4-figure table. So how do we do this? Usually it's called 4-figure tables because the entry of numbers in our table is usually 4 figures. So because of that, when we are looking up this value of this in a 4-figure table, we're going to pick the first two, and then under this third number, then the difference will be this fourth number. So in a 4-figure table, we have something like this. We have x like this. So x ranges from 0, 1. Okay, for logarithm, x ranges from 10. It starts from 10, 11 down to 99. So 11, 12, 13, 14, 15, 16 to 99. They have 1, 2, 3, 4 up to 9. And then you have a difference column. This is difference. Then you have 1, 2, 3 up to 9 as well. So what you do is that when you are looking for the value of a number, or you want to get the logarithm of a number, which in this case a, you want to get the logarithm of 6.895. The first thing is to determine the characteristic, which is 0 point. Then it is from the 4-figure table you are going to get the value of the mantissa, or the mantissa part. So when you get the mantissa part, you add it to, you join it to your characteristic, and that becomes the logarithm of that number. So now we've gotten the characteristic. The next thing is to get the mantissa of this value, of this number. For us to do that, since in our x column you guys have 2 figures, 10, 11, 12, so you pick the first two, disregard the decimal point, just pick the first two. We call it 68. So 68 under 9, you come to where you have 68, trace. So let's assume that this is 68. You come to 68, trace it to where you have 9, where both of them mix. The value here, what's the value here? You pick the value, you can write it aside. Let's say the value is, so let me look, this is my table, 68 under 9. Alright, logarithms of numbers. So I'm going to go to where I have 68. The 68, I'll trace it to where 9 is on this side of the table. So 68 under 9 is 8382. The value there is 8382. So the value here is 8382. This is 8 under 9. So the next thing is we have 5 here, which is the 4th figure. So that 4th figure will tell us where to look for, or what to pick next as the difference column. So what to pick next will be as the difference column. So let's say this is 5. We have dot here, so 5. So we come to trace it again, so where 5 is, and then look down. So what's the value there? 68 under difference 5. What is it? 68 difference 5 is 3. 68 difference 5 is 3. And the value there is 3. So what you do is that you want to add the value that you got from difference column. So the value you got from 68 under 9. So 3 add to 68 under 9. The value you got is 83 plus 83, 82. Or yeah, 882. So 2 plus 3 will give you 5, 8, 3, 8. So this becomes our mantissa, or the fractional, decimal fractional part. Decimal fraction 0.8385. So 6.895 is equal to 0.8085. So this is the number given to us, and this is the log value of it. So this is our log. This is the answer. So what we're asked to find the value of. So that's for A. So B is 68.95. So first thing is to determine the characteristic, and you can do that by merely counting the number of digits before the decimal point, which means we are interested in the integer when it comes to determining the characteristic. So in this case, the integer, the number of digits that make up the integer is just 2. And from what was stated when I was writing at the introduction, that the characteristic is obtained by noting that the number of characteristic is always one less than the number of digits that make up the integer. So the number of digits that make up the integer is 2. So 2 minus 1 is equal to 1. So our decimal, our characteristic here is 1 point. So 1, then you put a point. Another way to do it is express this number in decimal in standard form. So when you express this in standard form, it becomes 6.895 times 10 raised to 1. So the power of 10 is usually the characteristic 1. So this is 1. So the next thing is to get to find our mantissa. To do that, we're going to look for 68 under 9 difference 5, which is already what we have done. So that gives us 8385. Okay. So like I said, if you don't know how to get the standard form of a number, I've already done videos on that, so you can check those videos out on this channel. Just go to the search box and type in standard form, and the playlist will pop up, or the videos will pop up. Just take your time to watch them and get acquainted with how to express numbers in standard form. And even you can also get to know how to carry out calculations of standard form as well. So let's look at C. So C is 689.5. So what is our characteristic? For the integer part, we have 3 digits. So 3 minus 1, that's 2. Our characteristic is 2, or express it in standard form, 6.895 times 10 raised to the power 2. So which gives our characteristic value to be 2. Now next thing is to get the mantissa part, and to do that, 68 under 9 difference 5, which is 8385. D 6895. Our characteristic is 3 because there are 4 digits here. So 4 minus 1 is 3. Or you can start expressing standard form, which is 6.895 times 10 raised to the power 3. So 3 points. Then the mantissa part, 68 under 9 difference 5. That would be 8385. So that's one. There's something you need to observe, or if you've already observed it already, you discover that the mantissa is always the same for each case. From A to D, we have the same mantissa. So what changed, or what kept on changing, was the characteristic. So why? It's basically because when you're looking for the mantissa part, you do almost the same thing in each case. So what I mean is that apart from looking for the characteristic, which is determined by knowing the number of digits that make up the integer part and then subtracting 1 from it, every other thing you do is virtually the same. For instance, after you've gotten the value of the characteristic here, what you do is just 68 under 9 difference 5. You got B. First thing, determine your characteristic, and then the next thing you do is 68 under 9 difference 5. So virtually you were doing the same thing in each case when you were trying to get the mantissa part. The only difference was that you had to do something different when you wanted to know the characteristic, and that was why the characteristic is different. Another thing is that the characteristic could be positive or negative, but the mantissa is always positive. You will figure that out when we start looking at logarithm of numbers less than 1. So for now, this should suffice. We move on to anti-logarithms of numbers greater than 1. So what you need to know about anti-logarithms is that anti-logarithms are the reverse or reversal of logarithms. They are the reverse form of logarithms. Basically, what it does is that if logarithm, you are given a natural number like 2.347 or 2.347, whatever the case is, and then you find the value of this, the logarithmic value of this number. It could be 0. So these are 3 points. Any number, let me just assume 3.4892, and this is 0.4892. Okay, so now this is the natural number given to you, and this is the log value of this number. The anti-log is that you have to reverse this process to get this number again. And same thing applies here. Anti-log means there are processes you undergo to be able to get this number again. So once you do that, the result is called the anti-log of this. So this is the logarithm, and then this is the anti-log of this. So while at the beginning this is the natural number, this is the logarithm value of this number, then the anti-log is that this is the logarithm of a particular natural number. So you undergo the processes that to get the anti-log of that natural number, needs to be gone through, and then when you go through those processes, you get the natural number back, which is 2.347. So this is the log and this is the anti-log. The natural number you're going to get back is the anti-logarithm of the logarithm number. So it's basically same as, let's say, physical changes in chemistry. You get water, and then you add sugar, water plus sugar, you mix them up together, so it becomes a solution. So there's a physical process that this solution would be subjected to, and then you can separate the water from the sugar, so you get the water back and you can get the sugar back. So that's to say that the natural process, water plus sugar, is called water plus sugar to get solution. Solution in this case is like getting your log. Then the process you undergo, or the process you subject the solution to in order to get the water and sugar back, is known as anti-log. So it's a reversal. So that's the idea between logarithm and anti-log. So this is the natural number given to you. From this natural number you get your log. So this is the first process. It goes like this. Then from the log you get, the log value, you can get your anti-log, which is back to the same natural number. So it's kind of circle reversal. It goes like this and then back to this one. So that's what it is. So let's take example solution. So A. So find numbers whose logarithms are 1.8, 1.8385. So when we're looking for the anti-logarithms of numbers, this is logarithm. So I want to get back to the number that gave us this logarithm. That's what anti-logarithms mean. So 1.8385. For anti-logarithms, our consideration when we are starting off is not with this integer, is with the mantissa. So we're going to get the value of the mantissa by looking up these values in the anti-logarithm side in our 4-figure table. Alright, so just like the logarithm, we also have x in our anti-logarithm tables, and then we have difference column. This is difference. Okay, so here we have from 0, I'm sure, yeah, from 0. So, I think I made a mistake. In the logarithm table, it also starts from 0 to 9, not from 1 to 9. So the anti-log table also starts from 0, 1, 2, all the way to 9. Yeah, but the difference column starts from 1, 2, 3, all the way to 9. Same thing with the log table. So the log table starts from 0 to 9, anti-log starts from 0 to 9. But the only difference between the log table and the anti-log table is that for log table it starts from 10, that's integers, 10 to 99, while for anti-log table it starts from mantissa, the first 2 digits that make up the mantissa. So 0.01, 0.02, 0.03, all the way down to 0.99. So that's the difference. For logarithm, is integer whole numbers, the first two whole numbers. For anti-log is the first two decimal fractional numbers, which is 0.01, 0.02, 0.03 to 0.99. So what it implies that the first two numbers, which in this case 83, so you come, so here you have 0.83, and then you look up 0.83 under it, trace it to where you have it. So let's assume this is where it is. So you trace it down, trace it until it meets 0.83. So what's the value there? Let me look at my table. So 0.83 under it will give us, from our anti-logarithm table, 0.83 under it, 6887. That will give us 6887. So the value of 0.83 under it is 6887. So the next thing is to come over here and look at what the fourth figure is. The fourth figure is 5. So you come to the difference column. So let's say this is 5, and then you trace this down also and get the value that will be here. So 0.83 under difference 5 column, under difference column under 5. 0.83 in difference column under 5 will give us 0.83. The difference column under 5 is 8. The value here is 8. So just like in logarithm, so you're going to add this value to this value. So 6887 plus 8. So 7 plus 8 will give you 15. 1 plus 8 will give you 9, and 8. That will be 6895. 6895. So for the mantissa part, from our anti-log table, we got 6895. 6895. So this will give us 6895. Now you won't write the answer right away. 6895. Next thing is, now that we've gotten from our anti-log tables, we've gotten the value we've gotten this value just by reading off this value from the anti-log table. The next thing is that this characteristic here will determine where we put our decimal point, because actually this decimal point was gotten from the natural number by looking at the integer part. So for us to know where to put our decimal point, we are going to consider this integer here, which is 1. Now in log, we say that we should count the integer, the number of digits that make up the integer, and then subtract 1 from it. But in anti-log is the reverse. In anti-log, we note the value of the integer and add 1 to it. So here it is 1. 1 plus 1 is equal to 2. So if it were 2, just add 1 to it to be 3. If it's 4, add 1 to it to be 5. So now these values tell you how many times you have to move your decimal point forward from behind. So but in this case it's 1. So 1 plus 1, 2. So 2 here means that move it from here 2 places forward. 1, 2. That's where your decimal point would be. That would be 68.95. So that's your answer. Now when I started, there was this number that was on the board, and towards the end of that part of the board, we discovered that this, just like this process, from this number we got this. This was the natural number that we use as an example, and then we got this as a log value of this number. Now the anti-log of this log value give us this natural number back, which was the number that gave us this as a logarithm. So that was what I was explaining as a reversal. From the natural number you get the log value, and then from the log value you get back the natural number, and that process is known as the anti-logarithm of the number. So let's look at B. So B is 2.5714. So we don't have anything to do with the characteristic yet, this integer part yet, until we're able to get the value of this from our anti-log table. So what we do is 0.57. Always make use of the first 2 digits. Always make use of the first 2 digits. 0.57. So go to 0.57. 0.57. So let's assume that this is where 0.57 is. 0.57. So we're going to trace it down to 1 under 1. So 0.57 under 1. What's the value there? 0.57 under 1. 0.57 under 1 is 3724. 3724. So difference 4. So come to the difference column. Trace it. So let's say this is where 4 is. So bring it down. What's the value there? Difference 4. 0.57. 0.57 difference 4 is 3. So the value is 3. So we're going to add this 3, add 3 to this value. So 3724 plus 3. That will give you 3727. That's your answer. So the answer is 3727. Now this 2 you have here, like we did here, is going to be 2 plus 1 is equal to 3. So that tells you that you're going to move the decimal point 3 places forward from behind. So this will give us 1, 2, 3. That will give us 372.7. That's your answer. So this was a natural number that we got this logarithm value from. Actually, if this was given to you and you were told to look for the logarithm of this number, what would you do? You know, for you to determine your characteristic, you need to count the number of numbers, the digits, number of digits that make up the integer, and then subtract 1 from it. So in this case, the digits are 3. So 3 minus 1 is 2. That's why you have your 2 here. And then you now go to your log table and check for 37 under 2 difference 7, which would give you 57.5714. Now the anti-log of it is to reverse the process to get that natural number back. So to reverse the process, the first thing you need to do is not this whole number part, is the mantissa part. So you're going to look for 0.57 under 1 difference 4, which gave us 3727. Now this 2 here, for log you subtract, for anti-log you're going to add to this characteristic. So 2 plus 1 gives us 3, and that tells you how many times you have to move your decimal points forward, and your decimal point is assumed to be behind the first significant figure, behind the first significant figure. So move it forward according to the number of the value of the value you get here by adding 1 to the characteristic or the integer in your logarithm value, which is 2 here. So 2 plus 1, 3. So move it from behind 3 places forward. When you do that, it's going to be 1, 2, 3. You leave it here. So that's how we got this answer. So prove that if you are to look for the logarithm of this number, this is what you're going to get. I'll leave that to you as an exercise. Just do it and find out that if you are to look for the logarithm of this number, you're going to get this back, and then the anti-log of this will give you this back. So that's what I mean by the reversal process. And from here, to go into the topic deeper, we're making use of how to look for logarithm of numbers and also the anti-logarithm of numbers, both for numbers greater than 1 and numbers less than 1.